We are indeed very fortunate to have with us a scientist of the stature of Professor Vlatko Vedral. Professor Vlatko Vedral is professor at Department of Atomic and Laser Physics, University of Oxford. He is widely known for his research on the theory of entanglement and quantum information theory. He obtained his PhD from Imperial College in '98 and held a research fellowship at Merton College, Oxford, before returning to Imperial College as the governor's lecturer to start a quantum information science research group, a position he held from 2000 to 2004. Before returning to Oxford, he was Centenary Professor of Quantum Information Science at Leeds University from 2004 to 2009. He currently holds a joint appointment as a Professor of Physics at the University of Oxford and Center for Quantum Technologies at the National University of Singapore. He has published over 150 research papers in quantum mechanics and quantum information. He has held a professorship at Leeds, visiting professorships in Vienna, at Singapore, and at Perimeter Institute in Canada. He has over 7,500 citations to his research work and is the author of several books, including Decoding Reality. In the highly popular book Decoding Reality, Professor Vedral takes information as the most fundamental building block of reality and discusses what a useful framework this is for viewing all natural and physical phenomena. In building this framework, he touches upon the origin of information, the idea of entropy, the roots of this thinking in thermodynamics, the replication of DNA, development of social networks, quantum behavior at the micro and macro level, and the very role of indeterminism in the universe. It concludes by considering the answer to the ultimate question: where did all of the information in the universe come from? He is also investigating answers to several fundamental questions such as entropy, energy, and thermodynamics, harnessing quantum physics for improved information processing, and what does new evidence of quantum effects at the macroscopic level mean for us and the universe that we see around us, and new applications of quantum information going beyond teleportation, super-fast computing, and super-secure cryptography. These are some of the most interesting and challenging questions in science. Trying to find answers to these questions frequently challenges our very understanding of the nature of particles, time, determinism, and of the universe itself. His other books include Modern Foundations of Quantum Optics, Introduction to Quantum Information Science, and Introductory Quantum Physics and Relativity. He has won numerous awards and honors, including the Marco V. Jarek Award in 2011, Royal Society Wolfson Research Merit Award in 2007, and the World Scientific Physics Research Medal in 2009. All of us are eagerly waiting to hear Professor Vedral's address entitled The Power of Quantum Discord. Professor Vedral, please.
Thank you very much for inviting me to this excellent conference. It's an honor and a great pleasure to speak to you. It's a great pleasure to talk to you about something that's contemporary research. I've deliberately chosen something that actually has not yet even been published, and I'm very excited to speak about it. Rather than give you a superficial general overview, I'd like to tell you about something concrete that we've been doing. The first part of the proposal will really be motivating the whole setting, and I want to tell you a little bit about what quantum discord is. It's a kind of correlation that's neither classical in some sense and neither quantum entanglement, and it sits in between. And we are very excited now about this because we think that this kind of correlation can also be useful to us, and that's really going to be the main point of the talk. I entered the field in 1994, I think right when Shor's algorithm came out, and there was quite a lot of debate at that time about what's the effect that gives quantum computers the power that they have. The initial idea that it's really the superposition principle was quickly countered by the fact that we do have the superposition principle in classical wave physics as well. In electromagnetism, for example, we also superpose waves. So lots of people said it can't be the superpositions. It must be something more than that. And of course, entanglement is the obvious idea. Schrödinger said that this is the characteristic trait of quantum mechanics. This is the one that doesn't have any classical analog whatsoever. And this talk is going to try to go a little bit beyond that, to say that there may be something between these two, between the superposition and entanglement. And that's probably the best way to think about discord. The people I want to, I've been very lucky over the last 10 or 15 years to be surrounded by many smart people. And this is the current group. And I think the people I wanted to highlight are Felix Pollock, who is a current PhD student and Mark Williamson, who is a postdoc, then Mila Gu and Kavan Modi, who are postdocs. Most of what I will have to say is really based on our joint work. In particular, Kavan has led the project on Discord for a long time, and he's now compiling a RevMod phase that I hope you will be able to read within a few weeks or so, which is going to tell you much more about what I have to say. Here is the overview. I'll give a very brief intro into general idea of correlations in physics. I'll contrast how we think about correlations in physics to how we think about them in information theory. This is a usual point of confusion if you're a physicist and you come into this field. Then I'll say a little bit about entanglement in order to bring in this new kind of correlation which is called discord. And I'll try to explain to you where the name comes from and tell you a little bit of history. And then I'll talk about computational power of discord and information processing power of discord. This stuff that I will say at the very end are the two experiments that we've recently done in collaboration with Brisbane and Vienna. And we are excited about it that we have an information theoretic interpretation of discord as well. And then I'll say a little bit about the outlook. So the talk today will really be motivated more by information technology and computation than by physics, which you could also do, and you can talk about the foundations of quantum mechanics and the importance of correlations there. So in physics, of course, we use correlations in many fields, in solid state, condensed matter, certainly in quantum optics as well. You talk about various objects like Pauli matrices, if you like, for one object at site I and another one at site J. And then, depending on how these correlations scale, you can actually classify which kind of phase the system is in. So, you know, if you've got some exponential decay of these correlations, then we would typically say that we're in a disordered phase. Whereas if the drop is polynomial, then you would make a correspondence with an ordered phase of matter. Similarly, you can talk about modes, for example. You can talk about the output of a beam splitter, and you can have two different modes, A and B. And one of the important questions for a quantum optician is really whether there are any correlations in these modes. Can we decompose the 4-point correlation function into a product of 2-point correlation functions? And then we talk about different states of light, and we can talk about different properties in this way. So this is how we think about correlations in physics. And this more or less summarizes what I said before. If you want to witness, for example, a condensate of atoms, then you'd be looking at a creation of an atom at a point X, and you would look at an annihilation of an atom at a point Y. And then you would take these points as far apart as possible. So, of course, for a theoretician, this is infinity. In practice, you have a finite size of your system. And if this does not vanish in that limit, then you would say that you have some kind of critical system. So typically a condensate. This is what's known as long-range order. You can also talk about superconductivity if you put pairs of electrons together, and then you look at the creation of an electron pair at a point X and another pair at a point Y, and you test how this behaves. And if this still exists when you take the opposite ends of your system, then you talk about criticality again and being in an ordered phase. So this is a crucial way of talking about properties of systems in physics. And then, of course, outside of this, we also know that there are phases where this criterion fails. For example, in lower dimensions, in 2 dimensions, you have critical phases where only short-range correlations exist. And what is interesting is that now, so this is the topic I will only briefly mention, I will not really have the time to talk about it. Now we think that there are phases, people call them topological phases, where all of these order parameters fail, and you have to take entanglement as an order parameter. So the genuine quantum correlations would tell you then something that the conventional order parameters fail to tell you. So this is also an important direction, but I will not really say anything more about it. If you want to read more about it, there is another RevMod Phys. I like writing this RevMod Phys because you really get to say what you like in full detail without being compressed to 4 or 3 pages or whatever else we like to publish these days. So basically, this is a review that contains 1,000 references probably to this field. It's good to put you to sleep if you have problems falling asleep, I think. Now, let me say about information theory, how that comes in. Here is something that a solid-state physicist would also call an ordered phase. And a physicist would say, look, all of these spins are pointing in the direction up. This is your typical ferromagnet, if you like. And therefore, it's a highly correlated system, according to the correlation measures that I used before. But if you come from the information perspective, then this state is not correlated at all. This state is a product state of each of these spins being in a well-defined pure state. So let me tell you how an information theoretician would approach this problem. You would follow Shannon's approach to quantifying correlations, if you like. So this quantity is called mutual information, and I'm now looking only at 2 subsystems, A and B. You could think about it as 2 spins here, or you can think of it as one subset of spins versus another one. And Shannon would say what you have to compute in order to talk about correlations is you have to look at the entropy of A plus the entropy of B and subtract the total entropy of A and B. And if the systems are not correlated, then the entropy of A plus the entropy of B will be the same as the total entropy of A and B. And so the 2 will cancel, and the mutual information would be 0. And if you apply this measure to this state here, this quantity will always vanish. So as far as Shannon is concerned, and as far as we are concerned in quantum information theory, this state is not a correlated state at all. This has no correlations whatsoever. In order to have correlations, you have to have a certain amount of uncertainty in your state, and that's going to be the main message. So I'll give you an example, and that's going to be a nice way of introducing quantum correlations to you. So here is a state of 2 spins that an information theorist would consider correlated. In fact, this is maximally correlated as far as classical information theorist is concerned. So if you have 2 spins, but with a half probability both of them are pointing up, and with half probability both of them are pointing down, then you have exactly 1 unit, 1 bit of correlations. And the reason is the following. If you look at the entropy of the first spin, you have a probability 1/2 for state up and probability 1/2 for state down, and that gives you unit entropy. So this is 1. And by symmetry, S of B is also 1 unit of entropy. But of course, the main point here is that the total state is also uncertain because you have 2 possibilities, up, up, and down, down, both equally likely, so that the total state also has 1 unit of entropy. So if you put 1 here and subtract 1, you get exactly 1 bit of correlations. And this is maximum. And this would be maximum if the world was classical. And of course, the big mystery to us, and this is something that Vishal pointed out nicely, we're still arguing about and trying to understand, is that if you compute the same thing for a maximally entangled state, you will get twice as much. And you see, this really is very unusual. And there are many ways of saying that this is unusual. One is that this is something that you would call 100% correlated. And this quantum state would imply that you have 200% correlations. You know, how can that be? How can something be correlated 200%? Isn't 100% the maximum you can do? Another way, and this is what Schrödinger was very fond of, is to say that each of the subsystems is uncertain to 1 unit of entropy, but the total joint system has no uncertainty. It's in a well-defined physical state, up, up, plus down, down. It's a coherent superposition. So basically, this quantity is unit. This is a unit here as well, but the joint entropy of A and B is non-existent. It's a pure state. It's 0, which is why you get 2 bits of correlations. So it's very unusual from the classical perspective that a subsystem can be more mixed, more uncertain than the biggest system. You see, this is almost paradoxical. I mean, imagine, for example, that you're looking for your aunt, as I happen to have done some time ago. I have an aunt in France, and I wasn't quite sure where she was. So imagine I phone the local authorities up, and I say, I've got an aunt, here is her name, and she lives in Paris. And the police says, are you serious? You know, Paris has 10 million people. I mean, how on earth are we going to find your aunt in Paris? And then I say, oh, sorry, I'm actually not sure that she's in Paris. She could be anywhere in France. So it's very counterintuitive. And as you know, all sorts of Bell's inequalities and other features have come out of this to show that this violates this kind of stuff. So it's very intriguing to us. Now, the interesting thing for this talk really comes when you talk about mixed states. If you remain at the level of pure states, we heard yesterday, again from Richard's talk, that the division is clear. Either you have a state which is a product state, in which case it's nice and simple and it's very boring computationally speaking because it cannot do better than the classical state. And if you're guaranteed that you have a product state all the time in your computer, then you can simulate this with a polynomial effort, as we saw yesterday. The tricky bit comes if you have a mixed state. And here is a genuinely mixed state of n subsystems. And each of them has some label. So this is row subsystem 1, 1, and then it's correlated to the subsystem 2, 3, and so on. And P is a classical probability distribution on top. If you didn't have P, this would just be a product state that I was talking about before, and it would not be correlated. Putting this P on top correlates the state. And now the number of parameters you need to describe this state in general is an exponential number of parameters. And it's not clear at all that this is something that you can efficiently simulate with a classical computer. But here, on this slide, the question will be, if I'm given a state of many qubits, can I tell whether it's of this form or not? And it's a definition in our field that if the state is not of this form, then it's an entangled state. So I just want to show you how we treat entanglement very briefly before I proceed to Discord. So this state can be created by local operations and classical communication. And that's why we think of it as something that contains both classical and quantum features in some sense. Like I said, it's very tempting to say that this is also useless for information processing, but I will give you a counterexample to that in a while. So now, how do we witness entanglement? It looks like a very difficult problem. Imagine I have a typical solid with 10 to the power of 23 spins. And so this matrix would be 2 to the power of 10 to the power of 23 times 2 to the power of 10 to the power of 23. And imagine I ask you whether there is a decomposition of this type or not. It's a really hard problem, actually, and we don't really know how to answer it in general. So this is how we deal with that in practice. This is going to be mathematical, and I'm going to translate it into physics. So if you're thinking about a set of all states as some kind of convex set, and here is the yellow set, which are the states which are not entangled at all. So these are the states of this form. This orange set is just another complexity within entangled states, and I'm going to ignore it for the moment. It's not really going to be important for our discussion. So our problem is the following now. I have a given state here, and I want to know if this state belongs to this set or not. And if it doesn't belong to the set, then it contains entanglement. It's a genuinely quantum correlated state. So how do we deal with that? And fortunately, for some reason that completely escapes me, because I'm a physicist and I don't understand mathematicians very well. I really don't understand why they do certain things. But a particular pair of mathematicians. They're called Hahn and Banach in this case. They invented functional analysis. They considered the following problem. They said, imagine a point outside of a convex set. How do I tell whether this point belongs to the set or not? So the Hahn-Banach theorem, in a sense, deals exactly with this issue. I don't understand what their motivation was at all, like I said, but it's very useful to us. Now, this is something I'm told which is extremely difficult to prove mathematically, but to a physicist, it boils down to something obvious, and this is what it boils down to. If this point does not belong to the set, then there is always a line or a plane, if you're in higher dimensions, such that this point is on one side of that plane and the set is on the other side of that plane. So if the point doesn't belong to the set, you can always make a cut such that the set is on one side of this cut and the point is on the other side of this cut. I mean, to me, as a physicist, this looks like an obvious statement, and I don't even need to prove it to you, but I'm told that this is one of the toughest exam questions if you're a mathematician. Of course, I'm talking about discrete systems here. I think the continuous variable is the one that really becomes intricate. Interestingly, Banach was proving these things while drinking a lot of whiskey. He was very fond of Scotch single malt whiskey, and this is the only guy I know who could drink and derive mathematics at the same time. I don't know anyone else who can drink and do science. He was remarkable. Here is what this means quantum mechanically now, because I told you something highly abstract. Quantum mechanically, this line is defined by a Hermitian operator, like anything else in quantum physics. And what this says is, imagine I look at the average value of this Hermitian operator in this state. So I measure this operator many times in the state rho, and imagine that I get this below certain bound B. If now I do the same set of measurement on all the states of this set, and I get that they're above this bound, then this constitutes the proof that this rho does not belong to this set. So you can show nicely how this calculation of averages in quantum mechanics separates the state rho in terms of the average from the convex set here. And you can apply this sort of logic to any kind of correlation. It's just a very general method. Now, physically, like I said, it boils down to calculating Hermitian operators. And one example, and this really made a big splash when it came out, was in 2003. This is a kind of a salt that you take in a very small amount. You cool down to something like 5 millikelvin. So it's not a simple experiment. And then you measure magnetic susceptibility. You measure the response, magnetic response of this salt as you increase the external magnetic field. And the interesting thing is that the experimental data, which tell you how the susceptibility scales with temperature, can only be explained if you take the full quantum correlation into account. Here it says quantum entanglement. If you ignore entanglement, but you only assume the particular energy levels, then this won't do the job. And if you look at the classical, some kind of mean field theory calculation, this also won't do the job. So this was a big news in Nature. This was the group of Gabriel Epley at UCL in London. They have a big center for nanotechnology. And basically, this was the first experimental piece of evidence that even macroscopic objects at finite temperature can be fully entangled. This is an amazing thing, actually. So you can almost see entanglement in some sense. You can see the piece there. Now, this triggered some people like myself to say, well, look, magnetic susceptibility is something that people have been measuring for a long time. Can we find an earlier paper? And this paper was the earliest one I could find. Here is a paper, PhysRev from 1963, measuring, again, magnetic susceptibility as a function of temperature. So this is a paper that's nothing to do with entanglement or correlations or even Bell's inequalities. This is before Bell's inequalities, 1 year before Bell's inequalities, if you like. And you can actually now superimpose this witness, which is the red curve here, which says that all the points above are your separable classical states. And if you have anything below this red line, that immediately tells you that the state is entangled. So here we have direct experimental evidence that entanglement in copper nitrate here exists below something like 5 Kelvin. And 5 Kelvin is a very high temperature for a physicist. I mean, these days we can go down to a billionth of a Kelvin. So this to us is, you know, it's almost like room temperature. And this excited lots of people like me because it looked as though we can now have a room temperature quantum computer. I mean, what's all the fuss about? Why do we need to cool anything down if I give you a fully entangled state in a natural system at high temperature like this? Of course, I'm cheating a little bit. I'm being very superficial because this is, first of all, not the right entangled state. This is not as strongly entangled as we would like it to be. And secondly, making measurements on individual spins in this system may not be very easy, especially if you're competing with the natural thermalization process. But the point is that even in equilibrium state, when you're not manipulating the system, you can have entanglement in big systems. And that's kind of a motivation now for me, which is why I want to go into this direction of what kind of states do we need in order to have a quantum computer? How much can we get away with? It's not clear at all that if we ramp up the temperature, we're still not going to have good enough states to do universal quantum computation. So here is now the part where I will introduce Discord, and I will tell you a little bit more about it. So just to summarize, the states which are not of this form, now I'm looking only at 2 subsystems, we would call entangled states. If the state is of this form, then we call it disentangled or separable, but it's still not necessarily a classically correlated state. It contains more than classical correlations. And the reason for that is that this state here is in fact could utilize superpositions of different basis states. If I was to disallow superpositions and make it really fully classical, then I would arrive at this state here, which is really just a fancy quantum way of writing a probability distribution down of 2 random variables, A and B. So I'm attaching orthogonal states just to make it look like a quantum mechanical state, but this is really just a probability distribution. And all of these states are orthogonal to each other, and all the J states are orthogonal. So this would be a state like 0, 0, and 1, 1 mixture would be of this type. And this really is a classically correlated state. You can simulate it well on a classical computer, and you cannot get any quantum advantage. It's clear that entanglement, full entanglement, gives you quantum advantage. But what I want to talk about are these guys in between, where I don't allow coherence globally. I have no entanglement globally, but I do have coherence locally. And the question is this going to be useful for anything? And the gut reaction is that this should not be useful at all. So when I wrote about these states, it was very interesting because it was almost a rescue operation for a student of mine. She was my first PhD student. She came to me and she said, I'm very nervous. I'm already 2 years into my PhD and I'm not getting any results. And I said to her, why don't you look at this interesting problem of entanglement and classical correlations and take a general mixed state and see if entanglement plus classical correlations gives you the total amount of correlations, which is mutual information. So we knew how to quantify classical correlations like Shannon did. We knew how to quantify entanglement. That I did most of this stuff in my PhD. Actually, I did quite a lot of entanglement quantification. So it was very natural to see if these 2 things add up to total correlations, as you would expect. And what was interesting is that we found that for a general mixed state, if you sum up entanglement plus classical correlations, you will not get total correlations. You will get something smaller. And the excess correlations, that's why the name discord in some sense, because the 2 quantities are not really additive. whereas in classical information, these two different ways of quantifying correlations would be the same. So the discord comes from the fact that there is a little bit of discrepancy here. Namely, there is some quantumness here, but there is no entanglement. And the paper that we wrote, my student and I, this was 10 years ago, the paper that we wrote was completely unnoticed for about 7 years. I don't think there was a single citation on that paper in the 7 years that followed the paper. And then something remarkable happened, actually, and now we have an exponential number of citations, I think. We have something like 300 in last 3 years, and that's very interesting. And here is the reason why we have so many citations, okay? So here is the first evidence, as far as I'm concerned, that maybe there is something to these disentangled states which are still, in some sense, locally coherent. So this is a proposal by Neal and Laflamme, which says that for some computations, you can achieve exponentially efficient computation even when you only have one pure quantum bit in your computer, and the rest are maximally mixed. So this sounds like an amazing statement. I give you a universe in which all the bits in the universe are fully uncorrelated. They are really maximally mixed. They don't even have classical correlations. And that's the register here. And I give you only one pure qubit, and already this universe is capable of doing something exponentially more efficient than the fully classical universe. That's a remarkable statement. I don't have any intuition, really, behind it. I'll just present to you the mathematics. And then I'll talk a little bit more around it. So basically what happens is that this single pure qubit is initially in the state 0. It goes through an interferometer. But while the qubit is in an interferometer, you apply a conditional unitary gate on this completely mixed register of n qubits. So these qubits, of course, remain completely mixed on the other side because this state is invariant under this transformation. But there is a back action, if you like. There is a phase kickback into the pure qubit here, which gets measured in the usual way at the end of the interferometer. And the interesting thing is that what you get here, when you measure the probabilities for your state 0 and the state 1, what you're effectively computing is the trace of this unitary transformation un. So this quantum computer, with one pure qubit and otherwise completely mixed, is capable of computing trace of a unitary operator in a polynomial time. And you can see that classically you can't do that, even though trace is, of course, a very simple operation. It's just a summation of the diagonal elements of your matrix. The point here is that this matrix U acts on n qubits, which means that the size of the matrix is 2 to the power of n times 2 to the power of n. This is an exponentially big matrix. So it will take you exponentially many steps to calculate this, and it's basically inefficient classically. And then even more strikingly, and this is what the group of Carlton Caves noticed, the person doing PhD at that time was Animesh Datta, who is now doing postdoc at Oxford. And what they noticed is that even if you make this qubit as mixed as you like, but not maximally mixed, you will still be able to evaluate this trace exponentially more efficiently quantum mechanically. There will be an alpha 1 over alpha squared overhead, but if you fixed your alpha, no matter how small, this is still a constant overhead. And the punchline, what they noticed, is that if you make this qubit very, very mixed, then you will never generate any entanglement in this system whatsoever. So the statement is, I can have exponentially faster computation, but I guarantee to you that I never have entanglement in this system. And the group of Caves then went ahead and said, what can it be if it's not entanglement? And they identified quantum discord as the culprit. So the correlations here are not classical, they are beyond classical, even though they are not entangled. And so this was our first piece of evidence that you can do something exponentially more effectively than classically. Of course, in many ways, this algorithm is artificial, and it follows by no means that we can do things like search, Grover's search, or Shor's factorization in the same way. In fact, as far as I know, no one has been able to do that, and probably most people doubt that really genuinely hard problems will be solved in this way. But there is a class of problems which actually is easier on a quantum computer. So let me now say a little bit more concretely about information theory behind this, and I will very briefly describe the two experiments that I had in mind and I mentioned earlier. So this is not yet published, but the experiments have been done, and the next few slides are very mathematical, but I will be very brief when I'm talking about it. I'll give you just the gist of it. Here is a 2-qubit state where you have an orthogonal basis for Alice, psi 1 and psi 2. You have some probabilities for these states, and you have any two states, rho 1 and rho 2 for Bob. This kind of state you get if you, for example, do quantum cryptography, and you encode messages psi 1 and psi 2 into quantum states rho 1 and rho 2. Then the total state would be of this type. So this state is a funny mixture of a classical bit and a quantum bit. And if you look at it, in the logic of discord, it has no discord whatsoever. I mean, intuitively speaking, this is the state that we use for quantum cryptography, if you like, like the BB84 protocol. And you would expect that this is not really quantum state, precisely because we are doing classical communication with this kind of stuff. Now, don't worry about this. The main point will be the following. Mathematically speaking, you can tell that this is not quantum mechanical by computing the correlation tensor between the two qubits. So what you have to compute is xx, xy, xz, all the 2-point correlations of all the Pauli matrices that you can get. And if only one of these terms exists while the other ones are 0, when you diagonalize this state, then this state is only classically correlated. So, for example, if you only have the remaining correlations in the z direction, then your state is some kind of mixture of 0, 0, and 1, 1. And therefore, it contains no quantum mechanics. And that's going to be the main thing. Now, what is the protocol? And this protocol really surprised us. This protocol demonstrates that discord can sometimes do even better than entangled states. And that's really an interesting point. It's a protocol known as remote state preparation. So the summary is that Alice and Bob share maximally entangled states, or discorded states, or classically correlated states. It could be any of these states. And Alice makes a measurement on her qubit. And the idea is that she has to prepare a state on Bob's side in some well-defined plane on the Bloch sphere. So for example, they could choose the equatorial plane, and Alice has to make a measurement and project Bob's state onto one of the states on the plane. And the question is, with what fidelity can Alice do this? Incidentally, this was another way in which Schrödinger thought about entanglement. Schrödinger was amazed that if Alice and Bob share a maximally entangled state like this, then Alice can make a measurement to prepare any state on the other side for Bob. It's a little bit like quantum teleportation. He called it steering. So Alice can steer Bob's states to whatever state she likes. That's why we talk about non-locality in this case, because it looks as though there is an action at a distance there. Anyway, this is the game. And what Alice can do then is communicate one bit of information to Bob. Namely, when she makes a measurement, she can get two different orthogonal outcomes. And she communicates that to Bob, and then Bob can change the phase from plus to minus to align his state appropriately. And now, after a little bit of mathematics, which is probably not very relevant, the question is, with what fidelity, how well can Alice prepare a given state in a plane that's agreed upon between Alice and Bob in advance? And after some mathematics, which I don't want to really bore you with, the fidelity, the average fidelity in a plane, turns out to be the sum of certain correlations in this state that Alice and Bob share. So 1 is simply XX, this would be YX, ZX, and so on. This is this correlation matrix here. And the matrix, the sum of these 6 elements, tells you what kind of fidelity you have in a plane where you averaged over all possible angles in the plane. And the interesting thing is that the best fidelity that you can get in a plane, then minimized over all possible planes, taking the worst case scenario, if you like, gives you the sum of XX and YY correlations if you think of them as the 2 smallest components of that. And it's basis independent. So once you do all the averaging to find the best case scenario, suddenly your measurement really is independent of the basis which you're required to prepare. And these are the 2 lowest eigenvalues of the correlation tensor, and they happen to be exactly equal to the amount of discord that exists in this state. So they match a certain measure of discord that we have. And of course, if you don't have any discord, if you only have a classically correlated state, like I said, your correlation matrix looks like this, and basically there is no fidelity whatsoever. Now, the quantum discord seems to be now a resource as well. You can do this remote state preparation. And it's very different to entanglement, because entanglement is governed by the 2 largest eigenvalues of this correlation matrix, not the 2 smallest ones. So you can have an entangled state which is worse at remote state preparation than a disentangled one. And that's really the main point of this. And the experiment was done in Vienna with polarization of photons. This is actually a very simple experiment, because these days you can violate Bell's inequalities in 1 afternoon in the 2nd-year undergraduate laboratory. It's very easy to do that with photons. And in fact, this kind of experiment is very comparable to doing some kind of Bell violation test. Now, the last thing I want to say in the last few minutes is the second way in which you can think about discord in terms of information processing. And this is a completely different scenario at first sight, but you will see that it bears certain resemblance to the previous one. So basically, the idea here is that you have 2 people, you have 2 parties, and one of them claims to have a quantum computer. But imagine that this person is obviously highly secretive. I think we almost have an example these days, although the company I have in mind is now very open about it, and I think we're all invited to use the computer and even see it, and I know people who have seen it and so on. I'm talking about D-Wave. So basically, but imagine that the company is extremely nervous about you going and looking at that technology and copying the technology. So the question is, what kind of test could you give to them in order to see whether they can genuinely operate a large-scale quantum computer instead of just being able to manipulate individual bits, which is, of course, very easy these days. So here is the example with 2 different subsystems. And the protocol would be very similar to dense coding. It goes like this. You have again, 2 parties, if you like, Alice and Bob. And they have certain state rho. Now, Bob encodes something in a transformation, in a unitary transformation that he does on his subsystem. And that gives you another state, rho tilde. And now he gives both of these states to Alice, and he asks Alice to estimate what kind of operation was done here, what kind of encryption, what kind of message X was encoded there. And what you're trying to discriminate is whether Alice can really coherently manipulate this with a quantum computer, or if she only really has a classical computer and she can do individual measurements on these two subsystems. Obviously, if you really wanted to test the full power, you would have to generalize this to many subsystems and test it over many divisions. So this would be, this would be the estimation if you had a full quantum computer. And the message, of course, is that the estimated X is in general much more efficient if you could manipulate both of these systems coherently with a quantum computer. And the difference exactly tells you how powerful the computer is that Alice claims to have. And the interesting point is that the state which you need to use to test Alice does not need to be entangled. You can already see the discrepancy between quantum and classical if you use only discorded state. So separable state, but you use superpositions. And this was again surprising to us. So we don't need full entanglement to test Alice's ability to process quantum information. It's sufficient to remain completely separable. And the experiment, I will again describe it at a very superficial level. This experiment was done with continuous variables instead of polarization, instead of discrete. And what Ping Hoi and his group did in Brisbane was simply to take two modes of light, and you can think of them as coherent states. I wrote here coherent states alpha and alpha. And he modulated them deliberately in the same fashion. So he wanted to create a classically, something that's more than classically correlated, but it's not entangled. And the analog of a discorded state for continuous variables would be something that's correlated in one amplitude alpha or another amplitude beta. These are two different coherent states. So you can, in general, do some phase and amplitude modulation here. You can do the same phase and amplitude correlated in the other mode, and at the end of that, you can create a state like that. And then Bob can do his encoding, send this to Alice, and the two different cases are when Alice doesn't have the quantum computational power to measure these modes together. This is like a classical computer analog. And the other one is really to use a 50 beam splitter and few other optical elements here in order to make a joint measurement of these things. So this scheme just shows you that you start with coherent states, then you prepare a joint correlated pair of coherent states, then you encode in one of these subsystems, and then you send the whole thing over to Alice to make two different types of measurements, quantumly or classically. And the difference between the amount of information that you can get on this modulation is exactly equal to quantum discord. So it's an operational way of thinking about quantum discord. All of these things are really in preparation, and I think you'll probably be able to read about them in a week or so. So it's really very exciting for me to talk about it. I think I'm slowly running out of time. So let me just summarize, and I'll give you a little bit of an outlook. So what I really try to argue here is that it's quite likely that for a great deal of computation and information processing, we may not have to use the full powers of quantum computers. And this could be a very good news, because maintaining entanglement is in general very difficult. Usually you rely to cooling your systems down to very, very low temperatures. And of course, any noise there is very difficult to control for long enough. Or you rely on systems that hardly interact with their environment, such as photons. But of course, then they are not very good information carriers, precisely because they are very difficult to manipulate and get any computation out of them. Now, this line of thought would suggest that maybe we are working too hard in some sense, and maybe it should suffice to have superpositions locally, but not that much entanglement globally. Two things I want to say along these lines. We still don't know how powerful this is. So like I said, we can't do the two main algorithms that we always emphasize, factorization and search, cannot or we don't know how to do them in this way. Let's put it this way. But it's probably clear to many people that it should be difficult to do this even with Discord. The other statement I want to make is the mirror image, mathematically speaking, of this, which is that we don't know how to do this without entanglement, but we also don't know how to classically simulate states which are discorded and without entanglement. So both of these seem hard to us, which is why we think there is something more to Discord. The topic that I mentioned very briefly, but I really didn't go in any detail into, is, are these quantum correlations also useful for physics and not just for information processing? Can you really talk about criticality, quantum criticality, by using Discord as an order parameter? And this is really a big question now. And a lot of condensed matter physicists are excited about it because they believe that topological phases require certain techniques of this type. Another thing I didn't talk about is thermodynamical efficiency. So when Zurek introduced Discord a little bit later after my student and I did, he came from a completely different direction. He came from the direction of Maxwell's demons and how much work can a quantum mechanical system get more over and above classically correlated system. And he came up with the Discord in that context. And what's interesting there really is that if you think about certain types of entropies there, conditional entropies, they can become negative in the thermodynamical context. And this is very interesting to try to interpret them, because negative entropy should not really make any sense to us, given that entropy is a log of different number of possibilities, and it's got to be, according to Boltzmann's logic, a positive number. So here we have really hard time interpreting negative entropies, and I think there's a paper that we wrote recently where we tried to give a thermodynamical physical meaning to that. That's also related to Discord. And then, of course, there is the idea of unifying all the correlations and thinking about classical and quantum correlations and Discord all within one mathematical formalism. We also offered something like that, but I should say that these correlations still don't quite fit each other in the way that we'd like them to fit. Namely, we still don't get certain additivity properties about them and continuity, and we are not sure exactly about monotonicity under certain operations. So even from a purely theoretical perspective here, I think there is quite a lot of work to be done in this direction. Thank you very much for your attention.
So just wondering, who noticed the connection between the Neil Laflamme idea and your uncited and forgotten paper of 7 years ago?
I think this was the PhD thesis of Animesh Datta. The group, he was doing PhD with Carlton Caves in New Mexico. So that was the group. I think there are 5 authors on that paper. Animesh is the first author. It's his PhD work. I think Carl is the last author, as the head of. So that's the group that noticed the connection.